Okay, happy Monday, everybody. I'm here to give you a little more information about the second law of thermodynamics and continue our work that we did on Friday about second law. And this has been posted. These lecture notes have been posted and the slides have been posted on Canvas. We'll officially have a homework assignment that has to do with this second law stuff and the Kelvin-Planck statement that will be due on Wednesday. So stay tuned for that. I'll be posting that on Monday. I hope you all really enjoyed the experimental analysis from a hairdryer experiment that we did on Friday. I've had some questions from some of you about that and about mostly about how to find the exit area. Hopefully I sent out an announcement and everybody saw that, and we're able to calculate an area to some plus or minus error based on the experimental measurements that we took. So I hope you found that interesting and maybe enhanced your knowledge of the control volume analysis that we've been doing. Okay, so the next thing I want to do here is look at the survey results like I always do. This is the first question. The survey had two questions that had to do with the Kelvin-Planck statement and the Clausius inequality, or the Clausius statement essentially of the second law. As we noted before, that there is no exact law, second law statement like there is with energy. It's a little bit more nebulous and a little more difficult to understand. So that's why we're going to spend some time on it, and this whole chapter is kind of devoted to doing the proofs and correlations that go along with the second law. Okay, so the first question was what one of the following is correct interpretation of the Kelvin-Planck statement? Well, most of you got it right. It was that you can't do work by exchanging heat with only one thermal reservoir. We're going to mess with that a lot today because we're just going to keep talking about Kelvin-Planck statement and how we can use it to look at reversible and irreversible processes. A couple of you got it wrong. This one is the answer to the next one. So some of you actually put in this answer, which is the same as the correct answer. So all the answers were the same for the two survey questions. They just one of them was the answer for one and one was the answer for the other. So the Clausius statement says you cannot direct heat from a cold body to a hot body without work input. And maybe it was the same four people who had them mixed up. So it's quite possible you just had them mixed up. So most people got this. All right, this is as I said, a little bit difficult to understand, but I think you guys are doing a pretty good job so far in trying to understand it. And hopefully we'll see what comes out in the homework. Okay, so now let's move on to the lecture slides. So today I'm going to, let me get to the place where we got to last time. So we talked about thermal reservoir, we talked about Kelvin-Planck statement, and we also talked about the Clausius statement, and we did this example problem, which I've posted the solution to on Canvas today. I forgot to do it last week, but it's there now. Okay, and then so the next thing we want to talk a little bit about is, well, I'm going to talk a little bit about entropy first. We're not going to really define entropy until the second, until like essentially next week, or maybe later this week when I get into the next chapter, but in chapter 6. But let's just introduce the concept right here. So mass and energy are familiar examples of extensive properties that we use in thermo. Okay, as we know, mass is something that we do mass conservation, energy, we do energy conservation. These have become our kind of standard equations that we use for every analysis that we do. We're going to have a third equation that we use for solving thermodynamics problems after this, and it will be the entropy conservation, or essentially the entropy equation we call the second law. So entropy is another important extensive property. How entropy is evaluated is detailed in chapter 6, but unlike mass and energy, which are conserved, entropy is produced within systems whenever non-ideal things like friction are present. So things that are non-ideal, I mean things that generate loss. Remember, because we said that the first law says that energy is conserved, essentially such that the energy going into the system can be equal to the energy coming out of the system, and they're always minus some changes in the system's internal energy or kinetic energy or something. So essentially it's conserved. But we can say entropy can be produced whenever non-idealities such as friction are present. However, with respect to the environment, it's impossible for any system to operate in a way such that entropy is destroyed. So entropy is a very strange concept. It's one that I think we'll really dig into. And essentially, there's going to be a conservation law for entropy. You can produce entropy within systems, but that must mean that it balances within the system from a it must always be generated, and there's an equality that we can put together. But we're going to talk about that in chapter 6. So stay tuned for that. Now we're just going to talk a little bit more about these other things, that these non-idealities or non-ideal processes, right? So non-ideal processes, what are those things? We call those things in thermodynamics irreversibilities. So one of the important uses of the second law is to determine the best theoretical performance of systems, right? So where do we have what we call irreversibilities? So looking at the actual performance of something compared to some theoretical performance of something, we can get some insight into how we can improve the performance of a system, right? So the best idealized performance is evaluated in terms of some idealized process, and these idealized processes are called reversible processes. One in which we can go from one state to the other and either extract work or take out work, and go right back again by doing the same thing. So essentially, we can reverse a process, right? So we can go right back. Like, for instance, you expand gas through a turbine and you make work, and you take that gas and you push it right back through the turbine and you compress it through the same device, and you get back the same pressure and temperature that you came in with, right? That's a reversible process, one that you don't lose anything. It doesn't violate the first law at all. And it's a process that really can't be achieved, but it's the idealized process that we have, because there's always going to be losses. There's always going to be things like that we call irreversibilities in any system. Okay, so let's talk a little bit about what this means, irreversibilities. These are things that prohibit systems from being reversible, right? So those things are, so the short list, pretty much everything's irreversible, right? Everything we do has some sort of loss with it. There's friction associated with it, or there's some sort of heat loss associated with it, or something happens, right? So the types of irreversibilities that we see, and then we're going to see here, the first two are the ones that we're mostly going to be messing with. So the first is heat transfer through a finite temperature difference. Essentially means that if you got a hot block and a cold block, as we've said, and you transfer heat from one to the other, this process can't be done the other way, right? Okay, it can't be done the other way for free, right? You got to put something in to make it for free, and we're going to do a proof of that in our example problem today. And the other is, the other part of the example problem we're going to do today is that unrestrained expansion of a gas or liquid to a lower pressure. So we can't just blow gas from a high pressure place to a low pressure place without without incurring losses, because essentially we can't put that gas back without paying something for it, right? Just the same as the idea of a heat transfer through a finite temperature difference. Other things that include other things that we account as irreversibilities are spontaneous chemical reactions, like combustion, for example. Spontaneous mixing of matter, different composition or state. So you can take like nitrogen and oxygen and you mix them together. You can't unmix them, right? Just like when you make cookie batter, you can't put the eggs in, stir the eggs in the cookie batter, and then extract the eggs again without putting in some sort of work, right? You can't do that, right? You can't mix it up. You can't unmix things once they're mixed. That's an irreversibility, right? Friction. This is a classic one. In most machines and mechanical engineering, we think about friction as a loss. Friction is an irreversible process, right? You can't get back the work that you put into friction. You rub something, you have a sled that's rolling along a surface. You can't take that heat that you generated due to friction and shove it back in and get that work back. You can't. It's lost, right? So it's not possible to reverse that process. That's what we mean by irreversible. Okay. Other things that we have are electric current flow through a resistance. So electric current flow through a wire, for example, that's an irreversible process. Magnetization or polarization with hysteresis. So these are all electromagnetic stuff that you are also irreversible. Inelastic deformation, also kind of like friction, where you have elastic deformation may be reversible. So you take a bar and you bend it and it springs right back. That could be a reversible process, right? You could technically, if it were where if there were no heat loss associated with that, you could get that back. But if you deform the bar, there's not much you can do to put that bar back, right? I mean, you really have to remelt the bar down and then remake the bar again and make it exactly the way it was once you've permanently elastically deformed it. Okay, so these are all processes that are entropy generators, or that's what we say. So they're the irreversible process. So all actual processes involve effects such as those listed, including naturally occurring processes and ones involving mechanisms that we can construct on all scales. All right, there are irreversible processes on the very micro scale, and there are irreversible processes on the universe scale. Okay, and so these are this is a universal process. In fact, the idea of reversibilities in the universe leads to there's the idea of expansion of the universe and chaos, and all sorts of theories like that. So the idea that there's losses and that entropy is building in the universe in general is a sense that there's a sense of disorder, which is what we're going to kind of get to when we talk about entropy. Okay. All right. So let's see. During a process, irreversibilities may be present within the system, in the surroundings, within the system and the surroundings. So like what I mean by surroundings is you have your control volume, right? And everything outside the control volume is the surroundings. Things are inside the system is within the system, right? So sometimes you reject heat to the surroundings, for example. So you affect the surroundings. And those effects in the surroundings may be reversible or irreversible, right? So when we talk about entropy and we talk about irreversibilities, we're also talking about the surroundings. Okay, a process is irreversible when irreversibilities are present. Okay, that makes sense, right? It's totally logical. Okay, all processes are irreversible, actual processes. So in the real world, we always have loss, no matter what. There are no reversible processes that we can actually do, okay? A process is reversible. It's this idealized idea and not actually violating the second law. So technically, you could have a reversible process and still adhere to the second law. However, it's fully idealized. I mean, there's no way in our world that you can have. I don't think anybody's ever proven a fully reversible system. Okay, there's always going to be some loss to the system. Okay. But how much loss is there? That is the question. How much loss is there going to be? Okay, a process is internally reversible when no irreversibilities are present within the system. Okay, irreversibilities may be present in the surroundings. However, you can have a reversible process when it goes back and forth. However, you may have some heat transfer to the surroundings. So, for instance, you have heat transfer from some process that you take the same heat back in. But that heat transfer in the surroundings may be going through some finite temperature difference, which is causing irreversibilities in the surroundings, not necessarily the system. So an internally reversible process is called a quasi-equilibrium process, which is something that we've talked about already, kind of given the idea that we're at equilibrium at every step of the process. Okay, so that's what we talk about when we say internally reversible. Okay, not all quasi-equilibrium processes are internally reversible. All internally reversible processes are quasi-equilibrium processes, okay? Now let me say that again. So not all quasi-equilibrium processes are internally reversible, but vice versa is true, right? All the internally reversible processes are quasi-equilibrium processes. All right, just get that straight. Okay, because you can have a quasi-equilibrium process which is irreversible. So yeah, all right, one's a category of the other. Okay. So here's just an example we'll talk about. Let me just move myself here real quick. Water contained within a piston cylinder evaporates from saturated liquid to saturated vapor at 100 C. Okay. As the water evaporates, it passes through a sequence of equilibrium states while there is heat transfer to the water from hot gases at 500 degrees C. Okay. All right. So there's heat transfer going on and other things, right? For a system enclosing the water, there are no internal reversibilities. So for the system around it, there are no internal irreversibilities. But such spontaneous heat transfer is an irreversibility in surroundings, an external irreversibility. So the idea is that heat transfer to the water, there's not a Q in here. I like to put that Q in this diagram. So there's Q in here, right? But the heat transfer from the surroundings to the water to make water vapor is irreversible, right? Even though the process, if you take the system boundary around the water itself inside here, that process itself could be internally reversible, right? So you could recompress, once you put work back into this thing, you could recompress that water vapor and put it back in and extract the heat out. I mean, it would be fine, right? But the problem is that heat transfer that you have in the surroundings is an irreversible process. So we call that external irreversibility. Oops, I did that again. Okay, so let's move myself back to the corner. Okay, analytical form of the Kelvin-Planck statement. All right, so now that we've kind of got the idea of reversible and irreversible in our heads, let's think about how we can actually define the Kelvin-Planck statement a little more quantitatively. Okay, so far it's been like you can't exchange heat with only one reservoir and make work. Okay, so that's what we've said so far. Let's get a little bit more detailed. So for any system undergoing a thermodynamic cycle while exchanging heat with a single reservoir, the net work can only be negative or zero. It can never be positive. We can't get work out, right? We can put work in. That's no problem, right? So that doesn't violate. So for instance, here we have this thing that says, no, you can't do this. You can't lift the mass from this system, right? So whatever engine you have in here, or whatever this internal combustion engine exchanging heat with combustion and one reservoir, you can let the mass down and have work be done on the system and transfer heat, right? You can do that. You're putting work into the system by making this mass go down, and that work is causing some. You can just imagine the very simplest idea is that this mass is coming down. It turns some sort of grinding wheel, right? And the grinding wheel is generating heat, and we're throwing the heat into the thermal reservoir. We can do that. Sure. We can also do no work and just leave the mass alone, and this system works fine. It's a irreversible process, so I don't know, it works okay. However, we can't have work be greater than zero. Okay, so in this sense, the analytical statement of the Kelvin-Planck statement is work of the cycle has to be less than or equal to zero. Okay, that seems for a single reservoir. That makes sense. Okay. My goodness. All right, just move myself and fix myself in place here. Okay. All right. So, power cycles with two thermal reservoirs. So for a system undergoing a power cycle communicating with two thermal reservoirs, which is totally okay, according to the Kelvin-Planck statement, the thermal efficiency of a cycle is defined as this, right? So this is something we've done before. So this is work of the cycle over the heat that you put in, right? So work of the cycle is equal to QH minus QC. And so therefore, this becomes work of the cycle equals 1 minus QC over QH. So it's QH minus QC over QH, which you divide then by QH, and you get QC over QH, right? 1 minus QC over QH. All right, you can do that math. I think we've done this already in the past. A couple chapters ago, we did the same equation, all right? So this is something we need to know, but we're going to have to do it is we're going to have to figure out how we define the idealized efficiency of a cycle. Okay, so that's something we're going to work on in this chapter. Okay, by applying the Kelvin-Planck statement of the second law, three conclusions can be made. So the Kelvin-Planck statement is this: work cycle is less than or equal to zero. All right, first, that the value of the thermal efficiency must be less than 100%. Only a portion of the heat transfer, QH, can be obtained as work, and the remainder is discharged to the heat at cold reservoir. So, like if you had a completely reversible process, remember, then essentially there'd be no work, right? And so then QH would be zero, right? But you have to have, you can't have only one reservoir. Therefore, you must have some QC. And if you have QC, then your thermal efficiency has to be less than 100%. Because if you look at this, it would be 100% if QC equals QH, right? So. And you can't have QC equals zero. Okay, because if QC was equal to zero, you'd violate the second law, right? So if you say, oh well, QC is, I'm not going to have QC. QC is zero. Well, then there'd be 1 minus zero, which would be 100%. So that would be for a violator of the Kelvin-Planck statement. So therefore, that would be 100%. You can't have that. Okay. Okay. The two other conclusions are called the Carnot corollaries after Sadie Carnot. The thermal efficiency of an irreversible power cycle is always less than the thermal efficiency of a reversible power cycle when each cycle operates between the same two thermal reservoirs. And we're going to talk about this when we talk about the Carnot cycle, which is the idealized thermodynamic cycle that between two reservoirs. All reversible power cycles operating between the same two thermal reservoirs have the same thermal efficiency. Okay? That means that if you have reversible power cycles between the same two reservoirs, they always have the same thermal efficiency. Okay, a cycle is considered reversible when there are no irreversibilities in the system as it undergoes the cycle, and heat transfers between the system and the surroundings occurs reversibly, right? So that there's some heat transfer at a vanishing dt. Okay, so that's really not possible. Okay, so anyways, in actuality, it's not possible. But we have to define the idealized cycle based on something. And the idea is that you base it based on an idealized system, which is a reversible system, okay? Kind of an unobtainable system. Okay, so let's do a couple examples now. We're 21 minutes in, so I think I have time to do a couple. I have actually, here we go. I have an example that has two parts, okay? It's kind of funny. You hopefully don't get confused. There's gonna be some writing here. Let me get to my recording. Okay, so now use the Kelvin-Planck statement of the second law to show that the specified process is irreversible. Okay, as shown in Figure A. So this is the first part A. As shown in Figure A, a hot thermal reservoir is separated from a cold thermal reservoir by a cylindrical rod insulated by its lateral surface, i.e. if it's insulated, we call it adiabatic, okay? There's no heat transfer to the environment. But there is heat transfer down the rod, okay? Energy transfer by conduction between the two reservoirs takes place through which the rod remains at steady state. So there's steady state heat transfer going back and forth. So this is totally cool, right? You can do this. You can have a hot reservoir, some sort of like copper rod, and then a cold reservoir, and you're pumping heat from one to the other. No problem, right? And the cold reservoir could be like a block of cold stuff, and the hot reservoir could be a block of hot stuff, and you have a rod and insulation. This is totally okay. What we're going to try to prove, so let's just, oops. So what we're going to try to prove is that this is an irreversible process, known, is that we have a rod insulated, rod conducting heat from hot to cold reservoirs. Okay, what we're going to find is that this prove process is irreversible. Okay, what we're going to assume here in this process, there's going to be some key assumptions that we're going to make. So we're going to use the Kelvin-Planck statement about exchanging heat with one reservoir to prove that this is an irreversible process, okay? So the way we're going to do it here is that we're going to assume that the system, so the system receives energy from hot reservoir through the rod to cold reservoir, abbreviated, at steady state. It's not changing in time. Okay, 2, we're going to assume that the power, so that we can use a power cycle, some mythical power cycle, to demonstrate the irreversibility of the process. Okay, so now let's make our own diagram. Oops. Let's make our own diagram. Okay, so first we got this, I guess we're going to have some hot reservoir. I will just call this hot. And then we got this rod with insulation. Insulation I always draw with those little hashed lines like this. Oops, yeah, look what I'm doing here. And then we got a cold reservoir here. Okay, and our thermodynamic system is going to be like this rod. Okay, so this is our control volume, or our thermodynamic system, right? Actually, it's not a control volume, so there's nothing going through it. We'll call this system. Okay, so that's our system. There we go. All right, so now the analysis is to prove by contradiction. So we're going to prove by contradiction that the that the process is irreversible. Okay, what that means essentially is that we're gonna prove that if we made the process go the other way, that we couldn't do it without putting extra energy or extra work into the process. Okay, can't do it. All right, so here's what we're gonna do. This we're gonna use the power cycle to do this, to develop work by communicating with only one reservoir, thus violating the KP statement. Okay, and the second law, of course. Okay, so let's do it. So the way we're going to make this system then is, let's redraw our system here. So we hot, and we have cold. Okay, now we'll say our cold block is here, and we're going to have this rod, and we're going to have some power cycle here. Some power cycle. Okay, which is going to essentially do some, this is going to do some work. Power cycle. We can put it like an arrow in here. It's doing some work. Okay, and we have our thermodynamic system here. Let me just draw these lines here. So this is the rod. Okay, so now in order to prove this that this is a reversible process, so this is hot, we have to know that we can send heat the other direction, right? So the first process that we're going to have is a system that has a combined system that looks like the following. So it looks like this. This is our overall system here. We're going to just take this whole reservoir. We'll take the whole reservoir. Like this. Okay, so this is our new system, right? Okay, and there's our rod. It's still there. It's insulated still. So insulated. And even going to make these insulated too. Okay, so what we're going to do then is we're going to take heat. We're going to make a system that, oops, I'll do that. We're going to make a system that takes heat, some QH, and rejects Q to the cold body. So this is totally possible, right? This cycle is totally possible, this power cycle. And then what we're going to do is we're going to do the irreversible thing. The thing is they're going to take, or we're going to do the impossible thing. We're going to take heat and we're going to move it from the cold. We're going to move that same Q to maintain. So maintain the temperature constant inside this block. So in order to keep that block temperature constant and not have it be a non-steady state system, we have to be able to transfer that same amount of heat back to the hot body, give it back to the hot body, essentially. So take all that heat, send it back to the hot body, okay, in order to make it reversible. So, so the combined system can be described as this combined system is combined as it goes like this. So energy QH is transferred what to say? From hot to the power cycle, to the PC, okay, to the power cycle, producing work. There's work, right? And then discharging Q to cold reservoir. I'm just going to abbreviate here, okay? To cold reservoir. Okay? Now an amount of energy, and then the second part is then that amount of energy, Q, is transferred, so then Q is then transferred to H from C, and this would be, we'll say, would be possible if process were reversible. We'll say if the original process were reversible. That is, the original process is heat goes from the hot to the cold in a reversible way. If it was reversible, then of course this process 2 here would be totally possible. You could just take the heat and send it back, okay? No problem if it were reversible. Okay, so now if we think about that, now let's just kind of do the proof. So the proof in words. Right, the proof in words is that since Q is added to the cold reservoir at the process of the cycle, and the same amount of energy is removed from the cold reservoir. In the second process, the reservoir experiences no net change in its condition, meaning like the temperature. So C experiences no net change, right? So we'll just say A. C experiences no net change, right? The power cycle enclosed in the system also undergoes a cycle. So essentially, this system here, if I just redraw it, I've got my third page here. So we'll say B. We have now a system that looks like this. I'm just going to draw it out. So the cold reservoir is in there. We got the cycle. We got the hot reservoir. Right? It looks like this with the rod in it, right? And the hot is here, right? So essentially this then has a Q and QH. This process violates the KP statement because it's a cycle operating let's see, by making work by exchanging heat with one reservoir. I'm going to say no, can't do that, right? So that violates the Kelvin-Planck by the Kelvin-Planck statement, right? So this cycle is not possible. All right, so we know that C, then one of the two processes must be impossible, right? All right, it's clearly not so the power cycle is okay. 2, oh, I'm sorry, we call that 1, is okay, right? We can do that. We can do power cycle, right? The power cycle transfer to each, this totally, number one here is totally cool. So this is like process, we'll say process one, and then process two is this reversed. So the reversed heat transfer going from the cold to the hot. It must be the thing that's wrong, right? So we'll just say that the Q to hot must be impossible, which we know it is. You can't spontaneously transfer heat from a cold body to a hot body. No, you can't do that, right? So essentially that one or both of the processes are impossible. Therefore, the process involving the power cycle can occur. Then it's the process that must be impossible. So Q can't be transferred to the cold reservoir. Then, by definition, since you can't do that without putting work in, the original process, must be irreversible, right? Because you can't think of a way in order to get the heat to go back to the hot reservoir and get net work out of the process. So you can't do it. It's impossible to do it. Now, if you were to say, I'm going to put work into the process in order to do it, like for instance, you were to say, I'm going to take this power cycle and I'm going to heat up the cold reservoir and I'm going to pump that work back into the hot reservoir. You could do that probably, but then you're adding work to the process, so you can't do that, right? So essentially, this means that essentially this process is reversible. The original process must be irreversible. Okay, now let's go to the second example here. So the second example, 1b, is the same kind of deal, except that it's not a heat transfer question. It's a matter of free expansion, right? So it's a free expansion problem. So now we're going to use the Kelvin-Planck statement of the second law to show that the specified process is irreversible. The process looks like this. It's called a Joule's experiment. Okay, the gas, there's a container, okay, and it's totally insulated, so there's no heat transfer. It's adiabatic to the surroundings. It has a valve in the middle that's opened when you have the left side initially filled with gas, like some gas, air or whatever, and then expands into the right side and fills the gas until they reach equilibrium. Okay, now what we know here is we have expansion in a chamber through a valve. Okay, and what we do is we have to find again that the process is irreversible. Prove process is irreversible. Okay, this is called Joule's experiment. So Joule actually did this experiment in his laboratory. He had a tank and a valve with a long stem and this really super insulated tank, and measured it. It had thermocouples or some sort of thermal measurement devices on either side, and he opened the thing and he saw what happened, right? So what we're going to do is we're going to draw this out. First, let's make some assumptions. First, let's make some assumptions. One, we're going to say that there's spontaneous expansion such that gas fills both sides. Let's see, is there anything else? Yeah, during the process so there's no heat, work, change in kinetic energy, change in potential energy. Nothing else is happening in here, right? There's no work. We're not running any pistons or anything. So we have to say that. Let's see. Number 3 is that there's no essentially that there is a so we have available some sort of power cycle or turbine to use in proof. Okay, proof by contradiction again. So let's make our diagram again. We always have to make a diagram. So make a diagram. Here's our chamber. We'll make the first one is we have a valve, and we'll say this is evacuated, and this one's filled. This is at state 1, or state, we'll just say state 1. And state 2 is that we've got the same tank, and it's insulated. Okay. This one's insulated. Same thing, and now the valve is open, right? And then you have the same pressure. So the same thing phones up. So you have equilibrium. So you have the whole thing filled, and it's at equilibrium. Okay. So this is our diagram. This is our system at 1 and 2. Okay. So now the analysis is to do another proof by contradiction. Okay, so we're going to do is that we're going to use a power cycle or a device to make work. From a process. We're going to turn Joule's experiment into a cycle. Okay, but before we do that, let's think about the first law for original processes. So this is the original process, right? Right, where we have this expansion. So we have this stuff coming through the valve, and that it fills up the whole tank. Okay. First law for the whole process means that U2 minus U1, right, is equal to Q minus W for the process, right? We're neglecting kinetic and potential energy. I'm not even writing them in there. Okay. So since we said there's none of this and none of this, essentially we have U2 is equal to U1. Oh, interesting. What does that mean? Think about it. U2 equals U1, and it's an ideal gas. That must mean that T1 is equal to T2. That's weird, because if you think about it, the pressures on one side is high, and then you expand it out, and then all of a sudden the pressure goes low. So you have a change in pressure, but you don't have a change in temperature. We'll just say, assuming ideal gas. So that's kind of interesting, right? And this is actually something that Joule proved experimentally. So the internal energy of the system doesn't change. Okay? So let's modify the system. Okay? So we modify the system, and we'll do some additional processes. Okay, so let's do some additional processes. So how are we doing time? Oh, I'm running out of time. Okay, we're almost done. So we're going to say P1. So additional process 1 is we're going to let the expansion, so do the reverse of the free expansion. Okay, so we're going to move gas from left side. Was it left side? No, from right side to left side. Back to left. Completely. Right? We're going to, some magical process is going to take all the gas and send it back into the other side. Okay? Do that magically. This would be, we'll say, would be reverse of original process. Okay? So that's the first thing we're going to do. Then P2, the second thing we're going to do is that we're going to let part of the gas be part of gas be, so now we're going to go back the other direction. We're going to let part of gas be expanded through a turbine to do work, okay? And such that the expanding and doing work, we'll have essentially that work is equal to U2 minus U1, right? So we're going to have net work output. So U2 is then going to be less than U1. Okay, and then so then process 3, then in order to get it to go back and equalize the pressure to be the state it was when we did the free expansion, we need to add heat from a thermal reservoir to equalize temperature and pressure. So the way that the diagram looks like now is this. It looks like the box with the valve in it, and then there's going to be a turbine, which is going to do some work, and then it's expanding this stuff. So what you're going to do is process, and this is insulated still. Heck, you can insulate the whole thing if you want. It's fine. Okay, and you're going to do some work, and you're going to take this as your thermodynamic system now. Okay, this is my system. Now you're doing some work here with our turbine, Okay, and then what's going to happen is that you're gonna so process the original process, right? So the original process was called that process 0. Is that you open it up and then you went from which side you go? You went from the left to the right. So the process 1 is like 1 is free expansion, right? Or say 0. We'll call that process 0, free expansion. Process 1 would be you put it all back in there. You stuffed it all in there somehow, magical. So refill. And then 2, you took some of it back through the turbine. Back through turbine. But since then now you don't have U2 equals U1, you have to put some heat in. So let's just get rid of my insulation on this side. Okay, and we'll put some thermal reservoir here. Thermal reservoir. Well, I'm just gonna call it reservoir. Okay, some thermal reservoir, and we're going to transfer heat in. Come on. We're going to transfer heat back in here, Q. And so 3 is Q from the reservoir. Okay, so now we've got this whole thing, and it becomes a cycle, right? Because then you equalize it, and it's the same. So then you go all the way around in this cycle. So the cycle integral of heat equals the cycle integral of work, and heat equals work, and all this is great. Okay, so now the problem is, so if you did the proof, so the thing is that now you've got heat drawing from a single reservoir, and so the problem is that since the system, well, we'll say the cycle draws heat from one reservoir, it violates the second law. It violates the Kelvin-Planck statement. Right? Essentially, you've got this. See if I just make my dotted lines just the way I had it before, right? And then we exchange in heat with the reservoir. So we have heat and work. Can't do it, right? So we can't say this is no. Okay, so then B. So then since we did that, one of the processes must be impossible. One of the processes is impossible. So let's think about which one that is. Go back in here. So free expansion, yeah, we can do that. Refill, I don't know about that. Backflow, back through turbine, oh yeah, you can definitely send gas through at a high pressure back to a low pressure. That's no problem. Q from the reservoir, sure, we can do that, no problem, right? So the only one that's not, it must be the refill. That is not possible. Right? So since that's not possible, then you conclude that processes 1 is impossible. Since that's the reverse of the original, it follows that the original process is, so then we say C, so we say therefore original process, which we're calling 0, is irreversible. Okay, so that's how these proofs go. So essentially, oh good, I'm at 50 minutes. Okay, so essentially, let me just get to the bottom of this. It seems like a very contorted way to show that these systems are irreversible. However, in order, you actually have to go through the thought experiment to say, well, why is it that way? You know, when I get a letter from somebody who thinks they've claimed to do a perpetual motion machine, which I do get letters and emails and phone calls from people from Minnesota and other places telling me that they've invented the next perpetual motion machine. You know, you have to do these kinds of analysis to prove essentially, like, look, you can't have a process that exchanges heat from only one reservoir and makes heat. And you have to add some complexity. You have to do some thought experiment on it. And these kinds of proofs are the kind of ways that we do that in thermodynamics. Okay? I won't get you anything this hard for homework, but I will definitely have you look through the Kelvin-Planck statement and the Clausius statement and see what you can do about proving these certain things in your homework assignment for Wednesday. Okay, thank you.